Assalamualaikum and good morning.
Waalaikumsalam warahmatullahi wabarakatuh and good morning, Doctor.
Sorry to take your time for a while. Can you see my Excel form?
Yes.
Okay, just to share with you the marking scheme for, as you can see on the slide, is for brief project presentation and report submission form. So what we do, we put on your name, and then your supervisors will select who's going to present first. So you are not going to present according to your arrangement, but will be selected randomly by your supervisor. And then these are the criteria that we will look at during the presentation, as you can see here. So communication assessment is based on content, language, and organization and appearance. Okay. And then on the leadership and teamwork, on the participation and teamwork. Okay. And then management of knowledge on the present the importance of the project and its planning. So it's very important for you to organize the slides presentation and make sure that any of you or all of you understand the slides lah, so that any of you which apa ni been asked to present any at any part of it will be able to do so. Okay. On the report, there is three things that we will evaluate at this stage, which is the ability to evaluate info. So here we are assessing the effectiveness of you using all the information that you get, and how do you get into consider how you put in your consideration the public interest and social impact. Okay. And then also the ability to identify software. So as you know, it's identify software, so not yet the output that we expect, but at least you know where to start, or how you want to move forward from this brief report. Okay. And then demonstrate sustainability is to highlight the importance of the project and identify conclusion or implications and consequences to the sustainability aspect. Okay. So these are the things that we will look into, or your supervisors will mark each group lah. Yeah. And then let's see, is the rubric here. Brief rubric. Hmm. Where is the rubric? Okay, this one final. I will give you later. Rubric. Okay. Okay. So this is the rubric. Okay. For example, first is the communications, PO10. For example, PO10. I think this one the last one. So let's see where is PO10. PO10. PO3. Mana my PO10? Let me see. So just maybe try one. PO11 and how letak rubric tu kat sini. Mana pula rubric? What's the rubric to show you? 6, 8. Okay, right? Let me see if I have somewhere here. I should have saved it somewhere. Is that right? Tak ada. But basically, I'll give you the correct PO. But this is how we evaluate. For example, when we say effectiveness, either it is very ineffective, meaning that you present your work but you don't really understand how to achieve the goal, or somewhat effective, so average, or very effective. That means you are very sure how you want to move forward from the data that you have. This is, for example, for PO3 lah. But I will give you the details of this later on the PO. But this is sorry. But I want to highlight the this part first lah, basically, yeah, for your brief presentation, is that make sure that all in the group understand the flow of your slides, as the presenter is depends on your supervisors who's going to present first and last. And then the during presentation, this is the thing that you will see: the communication, leadership, and how you manage your presentation. And the content will be based on your report in details, as you can see here. So I'll pass this also to you for you to refer together with the rubric. All right, any question?
So basically yang marking ni supervisor je lah.
Yeah, supervisor will do the marking. You will record the presentation. I will see overall. So first mark is from supervisor, but I will moderate to overall lah, maksudnya semua group. Okay. So means that if probably some supervisor will give too high mark, where if I see from the other group, yours is not that good. So I will try to moderate and make sure that the marks is normalized lah. But the full marks is from your supervisor.
Okay, thank you.
So any questions? Okay. No question. I think that's all for this preparation to for the brief presentation and report. Thank you very much. So the speakers here already. Not yet. Okay, so with no questions, so we just wait for the speaker lah, yeah.
Assalamualaikum and a very good morning to speaker, lecturers and students. Before the event starts, please make sure that all of you turn on your camera and mute your audio during the talk session. Greetings to our speaker, IR Dr. Chang, and to the honorable guests. First and foremost, I would like to thank all of you for your attending this talk today. Before we start, let me share a little bit background about our honorable speaker. IR Dr. Chang obtained his Bachelor Engineering degree in Civil Engineering from University of Technology Malaysia in 2003. Upon graduation, he worked as project engineering in a geotechnical specialist contracting firm in Malaysia before pursuing his postgraduate study at Imperial College London, UK, where he obtained his master in soil mechanics. He obtained his PhD from the University of Cambridge, which was partially funded by the Norwegian Geotechnical Institute (NGI or ICG) and the Special Cambridge Malaysia bursary of the Cambridge Commonwealth Trust. He then returned to NGI, Norway as a postdoctoral fellow. He has experience in both offshore and onshore on geotechnical engineering. He is now a partner at DNP Professional Sdn Bhd in Malaysia. He is also currently the Secretary and Treasurer of the Geotechnical Engineer Technical Division GETD of IEM, the Institution of Engineers Malaysia. So, without further ado, I am pleased to invite IR Dr. Gue to enlighten us on geotechnical engineers in a construction project. Please welcome.
Thank you very much. Thanks for the kind introduction, Ms. Ainifatria. Can you hear me? It's clear, right?
Yes,
Okay, thanks.
clear.
Just let me share my screen. Okay. So I hope now this is on full screen on your computer or if you're on mobile. So okay, what I'm going to talk about today is actually on power foundation. I know that you have a slightly different topic that you have, but what I'll be actually focusing on power foundation on the industrial perspective on how we actually deal with power foundation from design to construction. So I know that now it's probably a bit still early for lunch. There's a picture showing a takeaway McDonald's here. Basically, I want you to actually focus on what you can actually take away out from this talk. So hopefully by the end of this talk, you may have a better idea on how to tackle power foundation designs. Now, I've been doing this kind of talk quite a few years now, not only in UPM, but also in other universities. And usually it is for the students integrated project like what you are doing now. So normally I'll get a question from students bringing along their bollock like this, and then they'll ask me what kind of pound foundation should be used. Now, if you have this question in mind, I would urge you to hold that thought for the time being. Why? Because this should not be the first question that you'll be asking, because you need to know what kind of structures you are dealing with, what kind of loading, and then you look into the soil profile and decide on what kind of foundation to be used. So it could be shallow foundation or it can be pile. So it's not necessary once you look in the soil profile and thinking of what kind of piles to be used. So let me just show you the brief contents on what I'll be sharing with you today. So I'll give an introduction on power foundation, and then I'll move on to show you on the procedures from starting of a project all the way from design to construction and testing, which is verifications. So you get an idea of the full picture. And then I'm going to talk a bit on design and construction, things that you need to be aware of for design and construction. And then continuing on common misconceptions, so things that you may have heard of, what are correct and what are actually wrong. And next I'll be sharing some of the construction issues and also ways to mitigate them. And then I'll give you a few case studies so you have a better idea on how our foundation is actually designed. And then a summary. So usually if I have this talk in UPM, I normally have a quiz at the end. But now I know this year it's a bit special because we are doing this over Google Meet or usually a video conference, a BC software. And I know it's quite hard to concentrate for a long period. So I've come up with pop quizzes in between the final summary and the quiz. Now don't worry, this won't be counted into your CGPA. So just hopefully you can concentrate and try to get as much as you can. So the pop quizzes and the quiz is just to gauge how much you actually get out from this talk. Now for the introduction, I mean not even for civil engineering students, even for laymen, we tend to admire how big or how tall and how nice a high-rise building looks like. But for geotechnical engineers, we are actually concerned what's underneath. And the most important question for us is on how to achieve effective and economical deep foundation. So hopefully by the end of this talk, you have a better idea on how to approach this. So the basic question is when to use power foundations. So we use it when we have inadequate bearing capacity of shallow foundations. Of course, we'll try to see whether we can use shallow foundations because that would be the cheapest option. If not, then we move on to power foundations. And also we use it to reduce excessive settlement and sometimes to prevent uplift forces. That means that sometimes you have high groundwater pressure pushing up your structure, so you want to withhold the structure to prevent the uplift forces. So these are the usual reasons that when we need to use power foundations. So I'll move on to the procedures. Like in universities, normally you would study each subject in detail. For example, this is a sample from a triaxial test. Of course, it's important for you to learn and how this is carried out and to get the soil strength and how the soil behavior. But very often in reality, of course, we need to tie in a lot of knowledge from different courses that we study in university to be able to actually perform or design a project. So I do not want you to lose sight of the big picture. So the following slides, I'm just going to show you typically what is actually done in reality for a project from beginning. So usually when we start off, we normally to carry out the desk study. This means that we'll try to find out the information, for example, what kind of project you're dealing with, what kind of structures, what are the loadings, where it is. So you can actually look into Google Maps and Google Earth. You can see the land. If you have a topographical map, you need to know whether that's a hilly terrain or a flat land. And also geological map. So even before going to the site, you have some information and some ideas on what kind of soil you're dealing with. And also, of course, if you can have information or soil information next to the adjacent site, that would be ideal as well. So once you do the desk study, then you actually go to the site, what we call a site reconnaissance or site visit. So you basically need to check the information that you get from desk study, whether it's representative in the site. So some of the things that are new from the information you get from the desk study. So you try to verify the information that you get from the desk study and see for yourself what is actually not captured in your desk study. So once you've done both of this, then you can plan for the subsurface investigation or what we call SI. Basically, you want to know what kind of profile or the soil profile underneath. Of course, this picture shows the SI man or the guy actually having his head into the ground. I'm not asking you to put your head into the ground, but actually we want to see what's in the ground, to know what's the soil profile so that you can design the foundation for the structure. So for SI, what we normally do, we'll have a few tests, and then we also obtain samples to send it to the laboratory and carry out lab testing. So once you've done that, then you get the soil parameters. And it's very important that I would like to emphasize here is that interpretations of soil parameters is important. So you're not only just getting the soil data from the field and the lab test and apply it. So you need to analyze and interpret the soil parameters. And once you've done that, then you can start to do design. So for today, I'm talking about pile foundation. In terms of design, which means that we need to select what kind of pile, what is the size, what's the length, what is the capacity, and also what kind of piling system. So once you've done that, you'll issue your construction drawing and you send it for construction. And during construction, it's very important to have supervision. So I'll explain a bit more that according to Malaysian bylaw, it is required to supervise the construction. And during construction, we carried out verification, which is testing, to basically verify the assumptions that you made during your design, whether it fits into your design or not. If not, then you probably have to revise the design and resubmit your design drawings. And sometimes if you have instrumentation in your testing, you can do optimization. That's where value engineering comes in. So you can optimize further your design to save more money. So that's typically the entire picture on how a project is being carried out from day to day in practice, all the way from desk study to verification and optimization. So in terms of desk study or initial information, what you need, basically you need to know what kind of structures you're dealing in? Is there any special requirements? So normally this kind of information will be given by the client, so they'll tell you what kind of structures they want to build. And then of course requirements, it could be authority requirements. And you also need the topographical map to know the terrain of the site that you're dealing with. And this is normally produced by the surveyor. And then as a civil engineer, of course, you need to propose the platform level to know how much cut or fill that is required. Typically, of course, earthwork, we try to balance out the cut and fill to minimize importing fill and exporting, because once you import or export, that will cost money. So you try to cut and fill within the land as much as possible. And also, you need to know the geology of the area so that at least you get some idea what kind of materials that you'll be facing at the site. And also what's very important, if you can get some previous data or case histories next to your site. I'll explain a bit more in the next slide why this is important. And then you carried out your subsurface investigation planning. So in terms of previous data or case history, so for example, in the middle, which is your proposed development, now if you have information from an existing development, let's say next door, so if you know what kind of soil profile, what kind of foundation that they have used, so if you want to develop this development, then you probably need less boreholes during your SI. If not, then probably you need more because you do not know what's actually underneath or next door. Now, things to look for at site when you have a site visit. It's very important for engineers to know what is the site constraint and the accessibility, because this will actually restrict what kind of machineries, especially for foundation. It's a big machine, so what kind of machines can get into the site. So a good engineer, when you go to the site, you then see what kind of access you have, what kind of constraint that you may have. So this will also impact and decide what kind of power foundations or any kind of works that can be carried out within the site. And also try to look for what kind of structures adjacent or features at the site, whether it's sloping, if you have a lot of boulders, or there be rivers, that again may affect your design. And adjacent activities, if next door there's another construction site, they are doing excavation, and how does that affect to your work? So this has to be considered as well. And also I have to emphasize more that even if you have your topographical map, it is important to confirm the topography and the actual site conditions, because very often in practice we find that even though if you have a topographical map, you may see that some of the areas may show that it's actually a flat area, but sometimes if you go to site, certain portion may not be captured in your topographical map. So that's why it's always important to confirm your topography with your dust study and the actual site condition. And also basically try to observe anything that may affect the design and construction of the foundation. So in terms of SI, of course, this one will be a big topic, so I'm not going into detail, but just to give you an idea that you need to provide sufficient boreholes in order to get the subsoil profile. And we'll carry out some in situ tests, that is to get the consistency of the ground. Typically, we'll carry out SPT, which is called the standard penetration test, or the bone penetration test, CPT. And then we carried out classification tests to determine the soil types, such as your liquid limit or plastic limit test, and your soil classification sieving test to know whether it's sand, clay. And then if you want to know the strength of soil, typically we carried out the triaxial test or the consolidated isotopic membrane test, or the CIU test. And if you have rock at the site, then you may collect the rock sample to carry out the strength test. Usually it's the unconfined compression test, known as UCT. And we also carried out typical chemical tests such as the pH, chloride content, sulfate content. That is just to see if there's any external elements within the ground that would actually react with your piles, for example, because your pile is also a concrete structure. So how would that impact to your power foundation? So that's why we also carried out some chemical tests just to verify. Okay, I'll move on to design and construction. Now, I won't go into detail, but I'm sure that your lecturers or your professors in your universities have taught you well on the calculation of geotechnical power capacity. But just to recap, For a single pile capacity, for the geotechnical capacity, it comes from the pile shaft friction, which means that it's the overall friction against the soil. It gives you the shaft resistance plus the end bearing. So the shaft skin friction and the end bearing gives you the ultimate bearing capacity. Now, what I want you to understand clearer here is that when we talk about power, allowable power capacity in practice, actually it is the minimum of two things. One, it's the structural capacity, and another one is the geotechnical capacity. Geotechnical capacity, like I mentioned, comes from the skin friction and the base contribution. But the structural capacity is just like a structural element like your beam or your column. So that basically the pile itself is a structural element. So you need to know what is the structural capacity. And the allowable pile capacity is the minimum of either of these. So just to show you quickly the simple equation for pile structural capacity, if you're using a concrete pile, it's given by 0.25 multiplied by the FCU, which is the characteristic strength of your concrete, multiplied by the cross-sectional area of the concrete pile. And if you're using a steel pile, then it's 0.35 multiplied by the U strength of steel and multiplied by the cross-sectional area of steel. And also we usually use pre-stressed concrete pile in practice. That's the equation. It's also 0.25, which is concrete. And then the FCU need to minus the pre-stress of the loss, and again multiplied by the cross-sectional area. So these are the typical equations for pile structure capacity. Now, in terms of pile capacity, in Malaysia, we typically do our design using the semi-empirical method, which is correlations with SPTN. The SPTN is the N number from the field test of the standard permutation test. So you can see the equation here actually comes from two parts. One is the Fs multiplied by the AS. So this one is actually your skin friction or skin resistance. And then the base. So basically the ultimate capacity, pouch capacity comes from the shaft friction and the base. So for the shaft frictions, we normally multiply it by the so-called friction factor multiplied by the SPTN number. And then it gives you the Fs, then you multiply it by the shaft surface area. And for the base, basically it's the base resistance multiplied by your cross-sectional area of the pile base. So you then ask, of course, what kind of factors that you need to do or need to use for your design. So typically, for single pile capacity, we use the following coloration. This is just to give you an idea on what kind of numbers or what kind of coloration to start off. It does not mean that this number is fixed, but it's from where you can actually start off. So for shaft friction, if you are looking into cohesive soil, which means that it's more clayey material, you can start off with 2.5 n. So it's 2.5 multiplied by the SPTN number. Whereas in cohesionless soil, for example, sandy material, then you can use 2n. And for the base capacity, typically you can use 250n or 9 times the SU. SU is the undrained shear strength. And in cohesionless soil, it's about 250 to 400 n. So these colorations are typically used for driven piles, and based on our research, sometimes that such colorations may be too conservative for check-in piles. So that's why it's very important that you start off with your design, but you actually do testing. And then if you find that you are too conservative, then you can revise and optimize further your design. And I also want to make you be aware that this is very important for you to know on base cleaning for board piles. Now, this is important because on textbook basis, they will tell you you can actually use your base capacity based on whatever material that your piles is actually sitting on. But in reality, this is actually quite difficult to achieve. And I'll show you why in the next slide. So base cleaning of piles is actually difficult, or basically there's no practical means of verification during constructions. So that's why in design, you have to use a minimal base contribution unless there is a proper base cleaning, such as grouting of the base. To illustrate the problem, so for example, this is actually a pile constructed, a board pile constructed, and the dashed line is actually a soil, and the brick symbol here is a brick block. So the problem is more prominent, especially if you have an inclined bedrock like this. So the red line is basically your casing for the board piles, basically to prevent the soil from falling in. But if you have an inclined bedrock such as this, you notice that some areas are not actually cased because the case cannot be different length, of course. So during the construction of board piles, in this area without the case, the materials of the soil will actually fall in to the base. And if you do your design, you may think that your base is actually rock, so it's a hard material, which you then use your rock properties, which is much higher strength than soil, to do your calculation, then you actually overestimate your base contribution. So that's why if you're using or designing board piles in practice, you have to give it a minimum base contribution. So typically in practice, we will limit up to about 10 to 15% of the power working load for the base. This another point is that I will actually share the slides at the end, so you do not need to screenshot or record any of this. So I will actually share the entire PowerPoint slides with you at the end. Now, I think to this stage, maybe it's good to have a quiz for a quick one. So you can actually scan the QR code here, and then these are the questions. So it's quite simple. You can just select which answer. The question is, what is the allowable power capacity? So in case if you are using, you do not have a phone, if you're using a laptop, I may copy link to the chat so you can click in and I'll be able to see the response. So you may click onto you can see the response now. So in the audience, we now have 59, including myself and Dr. Farah. So I'll be expecting more or less 50 answers. So far I'm only getting 5 responses actually, 6 coming in. While you're clicking to the answer, I'm just trying to check. Are you hearing clearly or is it too soft or is it just okay?
Yes, it's very clear.
Right, thank you. Okay, you can see we have now about 15 responses. Okay, maybe I'll just pull over my screen so that you can see what's actually happening here. So out of the 21 responses, you can see that majority of you have selected the allowable power capacity, basically the minimum of either power structural or power geotechnical capacity. So that is basically the correct answer. So majority of you have got the right answer. It's good. Okay, maybe I'll move on to continue with the slides. Now, understand that I mentioned just now for design on the shaft, you have different kinds of factors. So for your integrated project, you will probably need this as well. So you may say what kind of correlations to be used in practice? What are the typical values for design? For example, what is the shaft resistance factor? What is the base resistance factor? And also what kind of rocks socket friction if you're using rock. So instead of me going pages of pages and tables in terms of numbers, I'll straight away recommend you to the following paper. So this paper does not only give you the typical resistance factors that we use in Malaysia, but it also compares our Malaysian practice, which previously would be using British standards versus the Eurocode. This is particularly for driven power and board power in Malaysia. So here it gives you the typical values for soil and rocks as well. So you can actually scan the QR code to download the paper. I would also give you the link in case you are unable to scan it if you're using your phone for this talk. So I hope you'll find this useful. This paper will be useful for your design project. Now, moving on, I'll talk about the factor of safety, because when you design in engineering, of course, we'll apply a certain number of factor of safety for our power design. So in terms of the FOS, factor of safety, typically in the British standards, we normally do two kind of factors. One is called the partial FOS, which is partially for shaft and base. For shaft, normally we'll sum up all the shaft resistance divided by 1.5, and for the base, you will divide it by 3. And then that total up will be your allowable power capacity. And then you also carried out what we call a global factor of safety. Basically, that is to total up all the skin friction plus the base divided by 2. So you carried out both calculations, partial and global FOS, and then choose the lower one as your allowable power capacity. So this is basically the Malaysian practice when we are using British standards. Of course, I know that now we've moved on to Eurocode. So just to show you what's the difference, I know that UPM you've been learning on Eurocode, but in practice, some of us are still falling on to the conventional US. So it's probably good for you to understand what's the difference between these two. So the conventional, as I mentioned, will be carried out calculations on the partial shaft factor and base, and then another global, and you choose your lowest, and that is your allowable power resistance or your allowable power capacity. Now, in terms of Eurocode, it's slightly different. So from the ultimate power resistance, the first question you need to know is that will your design be verified by a preliminary static load test or maintain load test, sometimes you call it? So if you will be carrying out a static load test from after your design, if yes, then you will apply a model factor of 1.2. If no, then you have to apply a higher factor, which is 1.4. And then the next question they'll ask you is that would there be any explicit verification of SLS, which is the serviceability limit state? So meaning if you're carrying out more tests during the construction. If yes, you will again use a lower factor. If no, you use a higher factor. Similarly, if you're on this side, again, if you do more tests or verification of your SLS state, then you use lower factor. No, you use a higher factor. So what kind of factor? Of course, each country, for Malaysia, we have our own Malaysian annex. We can then refer to the Malaysian annex for the partial factors. Now, this is to show you some of the partial factors from the Malaysian annex for Eurocode 7. So what you can see here is that for EC7 Malaysian, we are designing for PALs. Basically, we are using design approach 1, combination 2. So you can see here it mentions that it's without explicit verification of SLS and with explicit verification of SLS. What it actually means in simple terms is that will you be carrying out less tests or more tests? So if you are carrying less tests, you will then be applying a much higher partial factors compared to if you're doing more tests, you're using lower partial factors. So basically, the Eurocode emphasizes on design verification, which encourages prudent engineering design. So if you do more tests, you know better on the soil condition, so you can be more optimistic. If you're doing less tests, then you have to be more conservative, and therefore you have to apply a larger partial factors. So these are again explained and also given in the paper that I've shared with you. Now, another issue that we normally face in practice is that the variation of soil profile. This is what we normally face for geotechnical engineers. Just to illustrate, the red line is actually, say, it's your project site, and normally within the project site, we have a number of boreholes that we carried out in the beginning. And the problem is that once you get back with your soil profile, it may not be so ideal like you have. It says that the soil is actually homogeneous and it's quite same. But here, what I want to highlight, you can see this is the pink color or the magenta color. This is within the same site. You can see the color here represents the hard layer. So some boreholes you can see very shallow, you already hit hard layer, whereas some very deep, then only you hit the hard layer. So the sites actually vary. So even within the small sites, the condition may be different. So these are the issues that a geotechnical engineer will face. So what can we do when we see such issues? So one way to overcome practice is that during our design, we can call it zoning or grouping of the piles to cater for this variation of soil. So for example, this is your building layout. These are all your pile points. So based on the soil borelogs on the soil profile, you may find that certain locations, let's say if you need 12 meters of piles, and some other location you may need 15 meters, some you may need deeper, 27 meters or 12 meters, or some shallower 12 meters. So you can actually zone out the areas based on the soil profile. It does not mean that you have a design that fits the whole site. So this is the one way that how we deal with variation of soil profile at site. Now it's important for you to know that what are the factors influencing your tile selection. So firstly, you need to know what are the tiles that are available in the market and also the typical installation method. Of course, there are some methods that are very advanced that may be in overseas. So if you want to engineer, if you want to specify those kind of methods, you can, but you will then increase the cost for the project because then it limits to the number of people who can do it. They have to probably import it from overseas that will increase your cost. So for engineers, of course, we always have to be alert in terms of cost as well. So you need to design your elements or your engineering aspects or the design has to be economical. And also to be aware of authority requirements. For example, if you are in KL, what kind of requirements? For example, DBKL would not allow you to use driven power because of the noise pollution. So you might have to think of other powering methods. So different states and different areas, the authorities may have different requirements. So as an engineer, you may need to be aware of where your project is and to be aware of the authorities' requirements. And then of course, you need to know the ground conditions. So for example, if it's limestone, then you may expect cavities and how to deal with it. And also I mentioned before the site conditions or constraint. For example, is the accessibility. So if the road is too small, the access road may actually affect what kind of machines can actually go in. And also to know what kind of buildings and magnitude of loadings that you are dealing with, and that also impact on what kind of piles that you will then select. So I mentioned the development program in terms of time and also cost. So this will also impact on what kind of piles that you'll be using. Okay, just to introduce you the typical piles that we use in Malaysia that you can actually normally find here. The most common, or one of the most common, is the RC square piles. This is your reinforced concrete. So the size typically is 150 by 150 to 400 by 400, and the length can be up to 12 meter per length, and it comes with 3 meter, 6 meter, or 9 meters. So if you want to join them, it's through welding, and the capacity typically can be up to 185 tons. Concrete grade usually 40, sometimes can be higher. And to install such piles, the installation method typically hydraulic hammer, which is driven, or chuck in. I'll show you what it means by chuck in later on. And the other very common pile that we use in Malaysia is called the pre-stressed concrete spun piles. The name spun here is actually the past tense of spin. So you can see the pile here actually have a hollow section. And the way they manufacture this pile, not only they pre-stress it, they spin it actually. So when they spin it, you get a hollow section in the middle. So that is where the name comes from, spun piles. So typically the size, they are circular. So diameter it's 250 to 600 millimeters. Some can be go up to 1 meter. And the length again varies up to 12 meters, 3, 6, and 9 meters length. And joints again is through welding. But here you can see that the capacity is much larger, it can be up to 394 tons, and the concrete grade can be grade 90 or 80. And installation method is same as your RC pile, which is through hammer or chuck-in. So you may then ask what's the difference between the spun piles and your RC square piles. So basically spun piles have actually a better bending resistance, higher axial capacity because they are pre-stressed and they're manufactured in the factory, so they have a better manufacturing quality, able to sustain higher driving stresses, higher tensile capacity, and it's also easy to check pile integrity, which means that after you install, you can actually send in an equipment to go in from the top to the end to check if there's any cracks within the piles. So this will not be able to be carried out if you're using normal RC square piles because there's no hollow section in the middle. And also in terms of cost, both piles are similar in cost. Usually the span piles will be slightly more expensive, but sometimes it can be cheaper as well. It depends on the availability in the market. So sometimes if the manufacturer they may have a lot of sun piles, so then the price may drop. But typically these two piles, the costs are quite similar. So in terms of pile installation methods, so there are typically three types of such piles. You can use either driving method, which is through diesel, hydraulic, or drop hammer. And another one is jack in, and the other one is pre-bore, then jack in. I'll tell you what is pre-bore then jack in. Probably this term it's not so familiar with many. Now, typically for driven piles or jack in piles, you actually check in to about SPTN value up to 50. So for example, a bore log profile here, these are numbers on your SPTN numbers. So engineers may ask themselves that in such conditions, should I use check-in piles or board piles? So check-in piles, like I mentioned, will only stop at SPTN 50. So what this means is that you can see here, these SPT values are more than 50, so your piles will only stop in the shallow depth. And the problem with this bore, you can see that down here is that there's actually some areas where there's softer material, which is less than 50. But your pile will only stop at this layer because you have an intermediate hard layer. So in such condition, of course, you can use board pile, but it will be more costly. So what we can do is called a jack-in or driven piles with pre-boring. That means that you actually drill through the hard layer, you bore through the hard layer, and then you check in your piles. So that is what we call check-in piles or driven piles with pre-boring. So you try to bore through the hard layers and then you drive in your piles. So this is to show you some of the pictures on how it looks like. So this is a diesel drop hammer for power driving, and this one is a hydraulic hammer. So these are the driven piles. Now in terms of check-in piles, the machine is quite big. As you can see here, the footprint is quite big because they need to have all the loads on top. So it's a counterweight. They need to use the counterweight to check in the piles into the ground. So piles will be checked into the middle. Now, if you want to imagine how these piles are actually checked in, I'll share you a video. So you can see that they wanted to check in these piles on top of the people here. They are actually the load. So you can see that the pile is not really going in because of insufficient load. So you can see another guy is standing on top and adding more load, and now the pile is being checked in. So that is the concept of check-in piles. Of course, this is not in Malaysia. We don't do this kind of method, but just to show you how actually check-in piles are actually carried out. So next I'll move on to board piles. So these are large diameter cast in situ piles, and the diameter can be from 450 millimeters in diameter to 2 meters. In some cases can be 3 meters as well. So the length it varies because it's up to you to pour into the depth you need, and there is no joint because there's only just one length, and the capacity you can see it's much higher. It's up to 2,750 tons. Concrete grade I show here is 35, but I think typically now we use grade 40 for most of our board piles. And installation method is drill and then cast in situ. So how is it done? So for example, if you mark out the location, pinpoint the location for your piles, then the board pile machines will be in position for the drilling, and then they'll start to drill or bore into the soil. And if your design you need to have rock socket, then you have to change the drilling bits to rock coring tubes to core into the rock. And once you achieve to the depth that you require, you will then move in your reinforcement cage of the board piles, and then you start to grab the pile using a trimmy pipe. You grab from below and all the way to the top, and that's a completed board pile. To show you the actual picture, so this is an example of a board piling machine. So this is the coring part. So this is in position for drilling. Once you have finished drilling, you're then lowering in your reinforcement cage and then start to grab the pile for the trimmy pipe, and that's a completed board pile. So if you are using board piles, some of the considerations that you need to be aware of is, like I mentioned before, board pile base is difficult to clean, and also there will be bulging and necking because the soil may overcome some soft and hard layers, so those issues may give you bulging and necking, and also collapse of side wall. So in order to overcome this, you may use casing for your board piles. And the other issues is that they usually, or we often see that there will be a dispute on level of weathered rock. So when you use board pile, of course, it's physically difficult for us to go into the holes that you drill through to see where you actually hit rock. So there may be a dispute when it comes to, the contractor may say that now this level 20 meters you hit rock. Engineers may say no. So that would be a dispute. So later on I'm going to show you how you can actually overcome this during construction and your design. Now, for you to understand when to use which type of foundation, you always need to keep in mind on these four issues. One is your cost, time, what's your site constraint, and also the soil condition. So with these four elements in mind, you then have a better idea on to choose what type of foundation. So in terms of cost, like I mentioned, there are a few types of installation method, from hammer, jack-in, pre-bore, jack-in, and then board piles. So this is to show you that the cost is increasing from driven piles all the way to board piles. So of course, in design, you start off, if you can use driven method, that will be most cost effective. If cannot, you probably need to use jack-in piles. If jack-in cannot be used, then you use pre-bore, then drive in or jack-in. If all these three you cannot use, then you have to resort to the last resort, which is board piles, which is one of the most expensive piling method. So that is in terms of cost. Some other issues in terms of driven power, it's basically the noise. So if you have been to construction site, the driven piles will be quite noisy and then there'll be vibration. So that's why for KL, the TPKL would not allow you to use driven piles. Then you have to consider, like for example, check-in piles or board piles. But even so, for check-in piles, there is also an issue which is the space constraint. Like I show you, the footprint of the check-in pile machine is very big, and you need a clearance of about 10 meters. Let me show you why. So for example, this is a site. So the red line is the boundary of your site. So this is the footprint of a check-in machine. So of course, typically you check in the pile in the middle of the machine, which means that you need a clearance of about 10 meters. So if, for example, your house is actually very close to your site boundary, we can still do what we call a site check-in, which means that you move the lever arm of the check-in to the side. But then, even if you use site check-in, you have to reduce your power capacity because of relying on the uh, lever arm, but you still need a clearance of 5 meters. So these are also some issues when you are using check-in piles. So if again your piles is very close to your boundary, then you may need to use board piles or micro piles, which will be more expensive of course. Okay, next I'll talk a bit about pile verification tests and why we need it. Basically, we will carry out pile tests, that is to verify the safety margin of your pile design to satisfy your limit state condition, and also to verify the settlement performance, that is to satisfy your serviceability state condition, and also to understand the load transfer behavior of each section of the soil and your pile, and that is basically more for optimization or value engineering. So just to show you what are the available verification tests that is commonly used in Malaysia, one of which is the static load test, or sometimes we call it the maintain load test. And if you have instrumented piles, then you can carry out the test with instruments in order to understand the load transfer behavior. So this is more for the value engineering. So instrumented piles can be within your static load test, or another one can be within your high strain dynamic pile test, or typically known as a PDA. So just to show you, this is a static load test or maintain load test. Probably you've seen this at the construction site. You see all these cartilage box, these are concrete box. Basically, it's the weight to load onto your pile to see the performance of your pile. So this gives you the most accurate and reliable result because your power is subjected to the actual load itself. And then you can know how it performs under the load and to see what kind of settlement that you may experience. So being said that it is the most accurate and most reliable, but it's time consuming. You can see you need to time to build up this whole block. So if you need time, time is money, so it's expensive to do such tests, and it also requires a big space. Just to show you a bit more on how it looks like inside this cartilage block. Inside, so the power is underneath, so you actually have a jack, a hydraulic jack, and you have instruments like your sensometer and load cell. So the jack will jack in the power so that the power will experience the load on top, and then you measure what kind of settlement. So if you're having an instrumented pulse, like I mentioned, if you have installed strain gauges and extensometers at different depths, then you can see the load transfer behavior of the pulse at each sections. So then you can see the performance of the pulse and the assumption of the soil parameters at different layers. Now the other one is the dynamic power test. So this is quite different from the static load test or your maintained load test. The dynamic power test is a method to obtain capacity and integrity through wave mechanics. So basically you will hit the pile with a hammer, which causes a downward stress wave into the pile, and the soil resistance will actually give you an upward stress wave reflections. So I'm not sure if you can see the animation here is that depends on your internet connection. So what I'm trying to show here is that if you have a hammer to hit the pile, the stress wave will go in, and because of the resistance of the soil, there will be a reflection. So based on the wave, you can actually analyze the pile top force and the velocity of the wave, how fast it goes up and down, and thereon you can actually calculate your pile capacity or pile performance at the site. So to show you a picture of the dynamic power test. So this is the piles and you attach the equipment. On the right here, you can see that the equipment, we have a pair of transducers and accelerometers. So these will give you the measurement of the velocity and the power force. You will then be able to calculate what is the power capacity of the actual piles that is installed in the site. Now, the benefit of dynamic power test is that many powers can be tested in a day, and it's much lower cost compared to the static load test. And pre-selection of powers is not required, and also minimum preparation. Of course, you probably need to prepare on the power head, and then you can test. Whereas for the static load test, you actually have to prepare. You have to select a power and prepare the area to build up the cartridge box. So these are the benefits if you are carrying out a dynamic power test. And also major defects can be detected because you can analyze the wave. It will also tells you if you have any cracks inside your piles. Now, having said the benefits, I would like you to notice that dynamic power test should not be replaced completely of your static load test. So typically correlations needs to be established, which means that in practice we'll carry out one or two static load tests, which is the one that we see to build up the cartridge box, and then you correlate with your dynamic power test. So then you can do more of your dynamic power test, but you need to have a correlation with the actual static load test. So it's not recommended just to carry out your dynamic power test. So the other power test that we have, not to get your capacity, but to verify the concrete quality, they are the power integrity test, which is having the same concept like your dynamic power test. So they use a smaller hammer to hit into the power, and based on the wave, you can see if there's any cracks. So these are called the power integrity test, or known as PIT. And another type of test, we call it the sonic logging test. And these are used to detect concrete defects such as honeycombing, if there's any cold joints or cracks. And these are typically installed on a board pile. So you can see the sonic logging pipes. They are small PVC pipes that are attached to the reinforcement cage of your board piles. So once you have completed your board piles are grouted at the site, so these PVC pipes are hollow, so you can actually send in equipment into these pipes. They will send in waves, and then you have a receiver on the other end. With that information, you will then get to know what is your concrete quality like, whether there's joints or cracks. So this has to be pre-installed in the reinforcement cage. So next I'll move on to common misconceptions for pile foundations. So what you heard is true or false. So the first misconception is that the pile achieves capacity when it is set. Set means when you try to drive in or jack in and then it stops at a certain load that you jack in. So usually that means that you have already achieved what you need. But whether pile achieves the capacity when it's set, and the truth is the pile may only set on intermediate hard layer, but may still not achieve the required capacity within the allowable settlement. Like I showed you the example before, if you jack in the pile, your pile may stop at the hard layer, but if underneath there is a softer layer, then later on when the load comes in, the soft layer will compress and then you experience large settlements, which means that you do not satisfy the allowable settlement. So it does not mean that the pile achieves the capacity when it's set. So you have to really know your soil condition. So the next misconception is that the dynamic formula, such as the Healy formula, will tell us the capacity of the pile. The truth is that the pile capacity can only be verified by using, like I mentioned before, the maintain or static load test or the dynamic pile test. So you don't just use an equation and do not need to carry out the test at the site and to know your capacity. So you have to carry it out either maintain load test and the dynamic pile test. Now the third misconception, this is an interesting one. So some people may say that the pile settlement at 2 times working load must be less than a certain magnitude, for example, 38 millimeters. So the truth is, the answer is no. If your pile is designed to a factor of safety 2, therefore at 2 times working load, of course you expect your pile to fail because you design it to a factor of safety of 2, unless your pile is under predicted significantly. No, but more important for you to understand is that the pile settlement criteria, it actually depends on your pile size, the pile material, whether it's a steel pile or concrete pile, and also the length. So therefore, it is unrealistic to adopt same settlement criteria, for example, 12.5 millimeters at working load or 38 millimeters at 2 times working load for all piles, regardless of length and size. It depends on the size, what kind of material, and your pile length. And it's also important for you to understand that there is actually a component we call it the elastic compression of piles. So pile itself will experience elastic compression. And the elastic compression is a function of PL over AE. P is the imposed load on your pile working load. The L is the pile length. A is the cross-sectional area of your pile. And E is the elastic modulus of your pile. So here you can see that if you have a larger pile working load or a longer pile, you will experience a larger elastic compression. Just to show you some of the actual recorded settlement of high-rise building, you can see some even go up to 125 millimeters. So imagine if you have large piles with high working load, then sometimes the elastic compression alone may be more than like 12.5 or 38 millimeters. So what is more important for you to understand is that actually distortion is more important than settlement. So what is distortion? Now, distortion is defined by delta over L here. Delta is the differential settlement between 2 points. So if you have a span, for example, of 10 meters and 2 columns in between. So what is the differential settlement between column A and B over a certain length? So that is the distortion. So this graph here gives you on the y-axis, there's actually 2 scales. So don't be alarmed by these 2 lines here. So one is actually in differential settlements in millimeters, and the other one is in inches. On the x-axis is the column spacing. Again, in 2 scales, one is in meters, one is in feet. So for example, if you have a column spacing of 8 meters, and let's say if your differential settlement is 25 millimeters, and that gives you a delta over L of 1 over 333. That is your distortion. So what this means is that here we show you if you have an angular distortion of 1 over 500, that is the safe limit for buildings where crack is not permissible. So that means that if you have any distortion less than 1/500, your building will not experience any cracks. And where the limit, where the structural damage is to be feared, is when you're worried that your buildings might collapse. That is when you have a distortion of 1/150. So in this case, for example, if your distortion is 1/133, what it means is that it's in between here. So you will have some cracks on your building because it's larger, the distortion is larger than 1/500, but it's less than 1/150. That means that your building is still safe, it won't collapse, but you will see some cracks. So this is why distortion is more important. If you have a building that settles together, so your column A and B goes down together, so your whole building will not experience any cracks. So that is why distortion is more important than settlement. Okay, the next misconception, some may say that jack-in piles cannot be used for high-rise buildings or limestone formation. And the truth is that jack-in piles can be used for high-rise buildings and limestone formation with proper design and input from experienced geotechnical engineers. So it's not to say that jack-in piles cannot be used for limestone formation. So I'll pause for a while for the second quiz. You can scan your QR code in case if you are using your mobile phone. I'll again paste in the link for you to click. So let's see if you can get this. Okay, I'm getting some of the responses in now. So the question is whether pile settlement at 2 times of working load must be less than 38 millimeters, else considered this pile is failed. So is it true or false? Okay, I'm getting a, quite a few responses in now. And do let me know if you need a break. I understand that the program that I was given, there's actually a Q&A in between. So if you have any question, by all means, while I'm waiting for the answer, so you can actually give me any questions. No problem.
Thank you so much, IR Dr. Gue, for your valuable insight on geotechnical engineers in construction project. Now, I would like to open the floor Q&A session. Any question?
May I ask, Dr. Gui?
Yeah, sure. Go ahead.
I've been long not with it, but I may know if the number of ballparks agreed proposed and
Sorry, Doctor, can you repeat the question? I think the initial part I can't quite hear it, probably due to the
how
reception.
how do we determine number of boreholes required and the position and how much per borehole?
Okay, so yeah, that's a good question. So typically for an SI number of boreholes, so it also, of course, it depends on the areas that you're dealing with. So in terms of buildings, we would say typically maybe a small, let's say one block building, you may have 5 to 6 boreholes. But it actually depends on the soil condition. For example, if you have a limestone, for example, then you may be worried on the cavities. So you may have more rock probing, so you may have more boreholes. The understanding is that you may need to give sufficient boreholes to know the profile. So if your site is actually highly variable, then you may need more boreholes, or else you need less boreholes.
How much per borehole?
Per borehole, if you include the strength testing, for example, the fracture test, you would say typically per borehole will give you about um, about 10,000, including tests, 10 to 12,000, including lab testing.
You shown just now in doing a check-in. pile, right?
Yeah,
There is some area if when we the jack in is only up to SP250, right?
correct.
Uh, is it because of the limitation of the jack pile itself or what?
Yes, correct. I mean, like jack in or even pivot, so there is a limit that you can actually jack in because you can try to have a bigger capacity to jack in your power, but you may actually destroy your power because
Oh,
of the limit of the structural capacity of the power as well. So typically we would not jack in or drive in when it hits about 50.
okay. And then since the case cannot be going, so there is a possibility that when you pour in concrete, the concrete go out of that area without the casing, isn't it?
You mean if you're using board power, whether the concrete will actually go out?
Ah, is it possible?
It's
Some
possible,
big.
especially when you have a cavity. So sometimes when you bore in, especially in limestone, so some people may concrete it because your casing typically won't go to the end. The casings are usually just the top area. So
Yeah.
some area which we have cavities, then the soil will actually, the grout will actually flow out to the cavity. So you may lose a lot of grout during construction. Then you know that there's something wrong. So probably you need to rectify it before continuing.
Okay. So that means what we can do is wait for the concrete to settle lah. Then we pour in on more.
Usually, we would try to do a theoretical calculation because if you know your length of the pile, you know what is the volume that
Yeah.
is required to fill in the pile. So that would be a good check whether the concrete that you pump in is actually correct or not. So that is what we should do during construction.
Okay. So that boring not necessary with casing lah. Some boring you don't need casing, is it?
Some boring you don't need casing. Yeah. If the soil is actually very good, then you probably don't need. But usually, yeah, you will need.
Okay.
And also when you drill, there's actually a bentonite fluid that will also helps you to hold the borehole
Oh,
without the casing. So
yeah.
that helps as well.
Okay. And then the static load test, is it compulsory for high-rise building for maybe there's a limit or is it compulsory for any kind of using pile?
I won't say it is compulsory, but it will be good to have it because, like I mentioned, if you use a dynamic power test, for example, then if you do not correlate with a static load test, then you may be concerned whether the dynamic power test giving you the actual reading because the static load test gives you the actual performance of the power.
Okay,
So typically, we will definitely carry out one or two because of the time and cost involved. So
okay,
for a small site, you maybe do one, or the larger site, you may do two or three, and then you do the rest on the dynamic power test.
right. Okay. That means basically, say for example, if there is a site where which uh, they already do some filing before and be left for some times, and then when we want to use the site again, uh, the static load test is must, isn't it? Because when you put in a new file, then you don't know how it connect to the old file, isn't it?
Yeah, then of course you need to verify what kind of design, whether it's from the same consultant, or maybe you're taking over from another design. Of course, then you may need to verify the designs. So yes, you need to carry out power tests for sure.
Uh, do if that's the case, do you consider the old one if you know the properties or if you know the earlier design?
Yeah, if the previous power, for example, the leftover, they have the power test, then you can actually use it. Yeah,
Okay.
yeah,
Possible if you have the data lah. If not, if it's not
yeah,
available.
yes, 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 of course.
Okay, okay. Thank you.
Oh, thanks. So let me just show you the response. So we have 42 responses so far, and most of you have got it right. So power settlement at 2 times working load must not must be less than 38 millimeter, and this is absolutely false. And as some of you have still chosen true, I'm not sure why. Okay, is there any other question?
Good morning,
Yeah,
Aya. Yeah, I have a question. It's just a general
sure.
question. According to one of your previous slides, you were saying about the requirements on the filing. So there were four reasons, which was one of it is cost, soil profile, another two more.
Mm-hmm.
So is it having the four reasons having the equal importance, or is it like one of the specific reason have more importance compared to the others? And if that's the reason, in terms of cost, is it stabilization is carried out first, stabilization rectification is carried out first, or in term of piling method is changed? That's all.
Okay, that's a good question. So actually, for an engineer, the first thing is to certify safety. So as long as your design is safe, then the other elements, I would say they are equally important, because sometimes the cost is definitely important, because in reality, every construction comes in about cost. So first thing is safety, and then the cost. So it all depends, like you see, let me just go back to show you the slides. So it depends. So, for example, maybe some site you do not site constraint, or depends on soil condition. So it actually depends on the condition. So I wouldn't say that one outweighs the other. But the most important thing for you to understand is that you must satisfy the safety, because in practice sometimes some of the clients or contractors, they may push you to the limit because they want to save costs, and your design may become too optimistic. So that would be a danger. So as a prudent engineer, safety is first and foremost.
All right, thank you.
Is there any other question? If not, then yeah,
Hello, sir.
yeah, sure.
Okay. Actually, I'm Kanda. We are from Group 10. We are given a task to build a sport complex.
Mm-hmm.
Okay. But unfortunately, we cannot go to the site, and then we also don't have the store profile. So in this case, we just know the geological structure under or behind our site is schist. So what is your suggestion? What we need to do next?
Because this is more of an academic question, because in reality, without soil properties, you cannot design your foundation. So you must have your soil properties. But I do understand that some cases, like in your project, your design project in universities, you may not have the soil information for your design. So my advice is that, I guess most of you have already done your practical training, is it correct? You are in your final year?
Yes, yes.
Yeah. So if you have some contacts from your place where you have done your industrial training, probably you can ask for the help to give you some soil profile, and then in your design project, you may can then explain that for your current design, you do not have the actual soil data, and then you borrow an arbitrary information, but at least you have some soil information for your design. So you can't say that just based on whatever geological information and then you do your design. So try to get some information and then explain it in your design project in the report, and say that you are assuming that this is actually from the site. It's best is that if you know that your site is, say for example, it's Candy Hill Formation, and you get the same kind of soil profile from any other site, and assume that it is from that site. But this is for your university project. But in practice, you would never do that, of course.
Okay, my question is, if we if we choose the price, how can we know the price? Because we need to do the estimation of the cost.
Yeah. So the cost is another thing. Of course, in practice, we also do quantity takeoff. I'm not too sure how much you learn in your university. That means there's a fixed cost for concrete volume, your reinforcement. So there on, usually in practice, there is also a quantity surveyor within the project. So we will then tell them what kind of piles, and then the quantity surveyor will actually measure the amount of concrete needs to be used, your steel. But if that is for board piles, for example, and if you are using driven pile, the RC pile or spun piles, then those are from the manufacturer, and they can actually give you the cost in terms of different sizes and length.
Okay, okay, I see. Thank you very much.
So if no further question, maybe I'll move on, and then if you have further question, I will then take it on at the end of the talk. Is that okay?
Yes, okay.
Okay, thank you. So next I'll move on to the construction issues. So one thing for a good engineer to have regarding construction issues is that you always ask yourself what can actually go wrong at the site. And the other issue is that with Murphy's Law, anything that can go wrong will go wrong. So my advice is that keep calm and be prepared for Murphy's Law. So we try to see what can go wrong. We try to mitigate as much as possible. Just to show you some of the pictures on issues that we found at the site. So on the left here, it's a power damage due to severe driving in soft ground. So make sure that the driving stresses does not more than what the power can take. So make sure that you specify the correct drop height and hammer weight. The other issues on the right here, you can see these are the defect due to poor workmanship of power casting. So if the piles are not casted properly, you may have cracks and gaps. So these are the piles that has to be rejected. You do not allow them to use it at the site. Other issues, and you will see on the left here, it's the defective pile shoes. So this you should not use. And again, this picture showing the problems of overdriving of the piles. You may get cracks at this. So again, it's important to make sure that at the site, what kind of driving stress that you are imposing on your piles. This has to be calculated and verified at the site. Another very important issue is actually pile stacking. So a lot of people that have actually overlooked this issue and how important it is. Now, just to show you on the left here, this is a right way of stacking the piles. On the right, this is not. Now, the reason this is not is because piles are typically designed to take axial load, but they are not designed for bending. So if you stack it like this, with improper stacking, you may induce bending to your piles. So when you have such kind of bendings, you may then crack your piles. So even the piles came from the factory, it was perfect, but if you did not stack it properly, then you may induce cracks. And if you're an engineer, if you go to the site, if you see the piles that are stacked at the site with issues with cracks, you have to reject them and ask them to give you a new set of piles. The other issue with pile stacking is that sometimes in construction, you may have insufficient space, so the contractors may put your piles next to a slope, and that would be very dangerous because you are adding additional load on top of the slope. So make sure that the piles are stored at the appropriate locations. So this picture here shows you some of the issues when you are having piles in the soft ground. So we call it the pile walking. Basically, if the ground is too soft, then the pile will actually tilt it. So to overcome this, you actually have to treat the ground first, or you have proper shoring to prepare for the platform and the area for piling to avoid such issues. So such issues are more prominent in very soft ground. The other issues with piling is the pile breakage, especially on inclined rock surface. So particularly if you are piling on a rock surface, if you do not have a proper pile shoes, so if you continue to join the pile, you continue to pile it down, and when you contact the inclined rock surface without proper shoes, if you continue to pile, then the pile joint will break and the toe will kick off. Continue piling, then the pile will continue to slide. So if you continue piling, this will keep on going down, but your piles are actually cracked or the joints are actually broken. So to overcome this, typically we use what we call an Oslo point shoe. This is also to minimize the damage on the rock. Just to show you that some of the piles or most of the piles or driven piles, they come with cast iron tip. So do not use such shoes when you are piling in inclined rock surface, because on the hard materials, you may fracture the rock and it weakens the base. So if you know that you have an inclined rock surface, then do not use such pile tip. Similarly for H section pile shoes, so this one again, you will actually fracture your rock. and you weaken the rock. Okay, another issue with piling is the presence of cavity. So I'm not talking about cavity in our tooth, but I'm talking about cavity in limestone. So the solution is that if during or before the construction, you actually need to detect the cavities through a series of cavity probing, which means that you're actually boring through the soil and try to locate the cavities. If you find the cavities, then you need to do compaction grouting to fill up the voids. Just to show you how it actually looks like if you have a limestone bedrock. So here you can see the dotted is actually the residual soil from limestone, and the blocky symbol is actually the limestone. So the features you have, for example, overhang block. So imagine if you have a pile sitting right on top the overhang block. If you additional load on top, you may then crack the overhang block and it may fall. Or you might have a pinnacle. So you may imagine if you have a foundation, if you sitting on top of this pinnacle, you may think that maybe my bedrock it's about, let's say, 10 meters underneath the ground surface. But if you just move slightly again, then you may drill all the way maybe another 10 or 15 meters, then only you hit the actual bedrock. So it's highly variable when you have in limestone. So you may have a pinnacle such as this, or you may have a floater block, and then a cavity. So if you're sitting on top of cavity, that would be very dangerous. And later on, you might have a sinkhole. So these are the typical features of limestone bedrock. Just to show you some of the cavities from actual limestone. So cavities can be quite big, and you can see this is showing you a scale of a human scale and the cavities. So if you have been to Butter Caves, for example, so that is also a limestone cave. So you can see inside limestone cave or cavity can be such big. So cavity in limestone is a challenge for geotechnical engineers. So make sure that you have to detect it properly before the construction. Just to showcase some of the issues now, if you are sitting on top of a cavity, if you do not know, you're not aware that underneath is actually a cavity, you thought you were sitting on rock. Later, when the load comes in from the building, you may then crack the cavity, and then boom, your house or your building may fall in, the building may collapse. So that is very dangerous. So during the SI or subsurface investigation and also the cavity probing, if you are dealing with limestone, so one of the way that we normally do is that we specify for 10 meters continuous coring. So which means that you need to core through, make sure that you have solid rock of 10 meters. So if you drill, for example, after 5 meters, you find a cavity, of course you need to ground it to fill up the cavity, but then you have to continue to drill it down and then you find another continuous of 10 meters to make sure that you're actually on firm rock without cavities. So that is typically what we'll do in practice. Now, moving on to field ground instead of rock, there are also some of the important points that you need to be aware if you're piling in field ground. Particularly, it's the high consolidation settlement if the original ground is soft. And you will also experience uneven settlement due to uneven field thickness. And you may have collapsed settlement or field layer if it's not compacted properly. And most importantly, if you are piling in field grounds and soft ground underneath, you may then have the negative skin friction, which is actually crushing. You have additional load which may crush your pile due to the high compressive stress. Just to illustrate what it means by negative skin friction. So typically for piles, it actually gives you the resistance that you see here, the green arrows. That is a normal condition. But if you have a layer of soft ground here, and if you add on load on top to the soft ground, and the soft ground will actually consolidate or compress, and once it compresses, it actually pulls down your pile. So it gives you an additional load that pulling down your pile instead of giving you a resistance, but your pile has an additional downward drag of the pile. That is what we call negative skin friction. And it's important that you need to reduce the power carrying capacity due to this. Now, if you want to imagine again what is negative skin friction, you can imagine someone is pulling down your pants, so that is negative skin friction is being pulled down. So in terms of design for negative skin friction, normally of course you have your shaft resistance. Some may say that because I've got soft clay layer, I know that it will pull down the power, so I ignore the shaft friction. But that is actually wrong. You not just ignore, but you need to account for. So you need to minus whatever that is actually pulling down your power, because that is an additional load to your power. So it's not just ignore, but you need to account for negative skin friction. So if this is not taken care of, then these are some of the effects that we've seen before, that the engineers have not catered for negative skin friction, and you get this kind of failures, which is quite serious. So to prevent negative skin frictions, what you can do is try to avoid feeling as much as possible if you are dealing with soft ground. And we carried out surcharging, which is ground treatment. Basically, you're adding load before you put in your building, so you allow the soft ground to settle, to consolidate first, and then you remove the surcharge on the load, so that the ground has actually experienced the settlement. So later on, when you put in the load from the building, it will not settle. So that is surcharging, is a form of ground treatment. And you can also sleeve the power shaft or apply slip coating. That means that you allow the ground to settle, but it does not pull down the shaft. So these are the things that you can also do as well. And most importantly, reserve the capacity minus for the negative skin friction, and also allow for larger settlement. Now, talking about soft ground, there are some engineers that they think that they maybe cater for it, so they power all the way to the hard layer, so they go deep down, they sit on the hard layer. But then they will have another issue, which is the surrounding soil may actually settle if you have soft ground. So, for example, you can see this is a gap where you see the piles due to the settlement of the surrounding soil. So the building is actually on piles where they're sitting on hard layer, but the surrounding soil, because of the additional load on top, it will compress and settles, and then you will see a gap. Some even you can see the exposed pile, which is ugly. But of course, the building is safe, but it will be unsightly. I'm sure you wouldn't want to be staying in such kind of condition, even though the building is safe. So just to illustrate, so this is what the conventional engineers may do on a low-rise building. So they may power all the way to the hard layer, and then the green is actually the soft clay. So if you have a fill material, which is additional load to the soil underneath, then later you have the black void, which is the settlement. So this void, you will then see that some of the piles may be exposed, like the photo that I showed you before. This is because they have actually piled all the way to the bottom. The structure is not settling, but the surrounding soil settles. So how to overcome this is that we can actually design our building on a pile strip, on a pile rough foundation. So this on the left is showing you the conventional system where they pile to the hard layer, and on the right is using the rough to spread the load, and you have shorter piles that are not piled to the hard layer. So why this helps? For example, after some time, the soft clay will actually settles, and then this one, on the conventional, your building will not settle, but for this particular one, you actually design it to settle together with the piles. So you can see that there's a gap. So the piles and the building settle together, so you won't actually see a gap between your buildings and the foundation. So you need to make sure that you calculate the settlement, you allow for it, and make sure that the differential settlement does not exceed the allowable distortion, so that your building doesn't crack, and design it to be settled together with the ground. This we call it sometimes the floating foundation. So I'll show you some of the pictures later on. Okay, another very realistic issue is pile deviation. So of course, ideally you want your pile to be in a specific location when you do your design, but in reality, world is not perfect, so there will be certain deviation. This is to show you some of the actual deviation of piles from a site. So this square is actually a column, pile cap for 6 pile groups. So the red lines here, these red circle lines is the actual position. So initially, of course, you want it to be in a nice position for the 6 pile. But after they pile, then you realize that the pile are actually deviated. So these are the arrows showing how much it has moved. So for example, this arrow here shows you it moved 360 millimeters in this direction and 128 in this direction. So these are the deviation at the site. So typically, what is the acceptable pile deviation? Of course, as an engineer, you cannot say that it has to be perfect, so it has to be deviated some sort. But what is the typical allowable deviation at the site is that for a pile group, or more than a pile, we will typically allow it to deviate up to 75 millimeters. And if you're having a single pile, that would be 40 millimeters. And then the verticality is 1 is to 75 deviation. So what happens if the actual site is more than the allowable pile deviation? So what can you do? What are the options for remedial works for such? For example, this one is 360, which is definitely more than the allowable deviation. So first thing, you would actually go in to check back your design. You can see whether there's any margin. So what I mean is that, let's say if your pile capacity is, say it is 100 kilonewtons, so you have 6 piles, which means that this pile group can actually take 6,000 kilonewtons. And typically a column does not come in exactly at 6,000 kilonewtons. So for example, the column load here could be 5,500. So you cannot have 5.5 piles. So that's why in design you put in 6 piles. So with the 6 pound, your column load is only 5,005, so you probably have a margin of another 500 kilonewtons. So with the deviation, then you have to work out what is the additional stresses induced on your deviated piles. So whether you're still in the margin. If yes, then you do not need any remedial work. But if no, then you have to seriously think of remedial work, such as adding more piles because now you're having additional load on the piles that you could not take. Then you have to add additional piles and then you enlarge your pile group for the entire group. And most oftenly in the site can be quite congested, so additional piles may not be able to be added. So the other way we can do is called using a tie beam to another pile group, which means that you construct another beam to transfer the load to another pile group. So that is what's called tie beam to another pile group. So you share the load between two pile groups. So these are some of the remedial works that can be done. Now, I also want to share with you that the piling supervision is very important. So when you supervise construction of piles, if you go to site, ensure that piles are stacked properly, like I mentioned before, and also to ensure that the piles are vertical during piling. And keep proper piling records. This is important because whenever you have problems, you may then be able to check back the piles, what has been done for that particular pile, and then try to figure out what's the issue. Without proper piling records, you may not be able to figure out what's wrong and how to solve the problems. So proper piling records is important. And also very important is to ensure that the correct pile types and size are used because in your design, the engineers might have done a lot of calculations, should be correct, but at the site, if they use different pile types and different sizes out from your design, that would be a disaster. So supervision is to ensure that the site construct as per your design drawings. And also, it's important to ensure pile joints are properly welded with no gaps, and to ensure that you use correct hammer weights and drop heights, or else you'll be having too much stresses on your pile and you may damage your pile. Now, this is also quite interesting that throughout our experience, we found that some of the contractors at the site, they may cheat in terms of pile length. This is I'm talking about board piles, where they actually tempered the measuring tape. So what this happens is that when you go to the site and then you wanted to check the depth of the board pile, so the contractor may hand you a measuring tape and then you happily measure the depth and you may see that this pile depth is about 20 meters. But little did you know, maybe the measuring tape has been cut off. So maybe they've cut off 5 meters and then they stitch it back. So on the reading you saw it's actually 20 meters, but actually it's only 15 meters. So that could be a problem. So our advice to engineers is that always try to bring your own measuring tape. That is to avoid tampering of measuring tape. And another issue is the cheat in rock coring. Now the reason is that the price for coring in rock is about 10 times the coring in soil, so it's very tempting for contractors to say that they've already cored into rock so that they can claim a coring rate for rock coring instead of soil. Now to overcome this, we have actually recommended a few definitions to fulfill to say that they actually core into rock. So these these criteria are actually spelled out in the construction drawings. So first, you must make sure that they change the tools from rock coring tools. So for example, when they start boring in soil, if they go into rock, they will need to change the tools because you cannot use the same coring tools for soil and in rock. So at the site, make sure that they change different coring tools for rocks So change your coring tools. And next is that the once you core into the rock materials need to be verified by carrying out a point load test. It depends on the rock condition. So in the design, we have set certain criteria that the point test to achieve a certain minimum index test. And also very important to make sure that the rock materials are actually from the boreholes, because we also see some cases that you do not have a full-time supervision, you may be walking around, and then they will throw in some good materials into the borehole, and then they take it out and show you that they carry out the point load test to achieve the strength test. So make sure that the rock materials are actually obtained from the borehole itself or from the hole that you make from the bord pile. And also, the recovered rock materials should be more than 70%. Depends on site condition. Typically, the rock materials in that area, that depth, should be 70%. So to fulfill all this definition, then only you can quantify that they are actually coring in rock. So with this kind of definition, you can try to prevent cheating in rock coring. So it's important to have proper supervision at the site, so we're not sending a scarecrow just to send someone there. We're not doing things. So this is not what we want. What we want is to follow standard operating procedures. And most useful is that to have checklists, because we engineers or site supervisors are still humans. We may still tend to forget some of the things. There may be mistakes. So if you have a proper checklist, then you won't miss out any points. You can tick things that you've checked. You can take it off. So with the proper checklist and following standard operating procedures, that is to carry out proper supervision. So failure of supervision may then result in higher instances of power damage and also wastage or sometimes failure. So it's very important supervision has to be carried out. And just to let you know that according to a Malaysian uniform bylaw, what is summarized here is that the design engineer must supervise the construction. That is according to the bylaw. So you cannot say you just design and you don't care what's happening at the site. So the design engineer must supervise the construction. Okay, so I will now move on to some of the case studies. Basically, I'll go into detail on one of the case studies so you have a better idea on how to do your integrated project. And the other studies, what I'm going to show you is just the key points and the essence of from the case study, and basically how value engineering can be carried out. So I'll go in one into detail, and the rest would be just going into the key points. So the one that I'm going into detail for the case study is actually a multi-story park and ride building for the MRT Line 1 Sarjana Impian station, which is in Kajang. So this is not too far from the UPM. So this dotted line is the site, which is quite close to Tesco Kajang. So if you zoom in, the site, there's actually two phases. So the blue one here is phase 1. There are two zones, zone A and zone B. The MRT station is in the middle of the road here. So these two zones are the park and ride stations. Phase 2 is not yet developed, so it's for residential. So what we've done is actually for phase 1, which is zone A and zone B. Now when you have the site, then you look into the geological map where your site is actually located. So the site is actually located in what we call a Kajang formation, which means that the formations with schists with minor intercalations of limestone and phyllite. So what I want to highlight here is that the area is with limestone. So when we talk about limestone, we are concerned of cavity. So once you have limestone, you have to be alert to check for cavities. Just to show you some of the boreholes from the site, what I want you to bring you to attention is that this site particularly, the soil varies a lot. So the red circle shows you the softer layer with the smaller SPT-N number, and comes with also a hard layer with high SPT number. And in between the hard layer, you can see there are also some soft layers. And also we have limestone and granite. Now this is not really a good example for limestone borehole, because typically for SI in limestone, we would definitely recommend a 10 meters of continuous coring like this one. Then you know that there is no cavity. So this one is fall short of 10 meters, so there is a risk there's actually a cavity underneath which we do not know. And also you can see besides limestone, there's also granite here. And bear in mind that all these boreholes are actually quite close to each other. And you can see that some area you may face limestone, some you may face granite, and some you may hit the rock. And but other boreholes, which is just a few meters apart, go to the end, you can still not see any rock. So the site condition is highly variable. And in such condition, then you may think of what kind of foundation can be used. Of course, this is a multi-story car park, so the load is actually not light, so the shallow foundation will not be able to sustain the load from the building. So then you start off with thinking whether you should be able to do a driven or check-in piles. Like I mentioned, the check-in pile may stop at SPTM 50, so you'll stop short at certain areas. And then you see that underneath the hard layer, there will be soft material. So then you consider, okay, I can't just do a check-in pile, then maybe I need to do a pre-boring or check-in or driven. But then the other issue is that some areas immediately you hit rock. So if you're doing pre-boring, you make sure that how can you make sure that now just the hard layer or then it's rock. So the site is highly reliable. End up we have decided to go for the expensive option, which is the board pile, unfortunately. So in terms of board piles, we have actually selected four different diameters of board pile, which is from 600 diameter, 900, 1002, and 1005. So we're using concrete grid of 40. This is the cross-sectional area of the piles. So then you can calculate the allowable structural capacity, which is 0.25 multiplied by FCU and AC. So this is the allowable structural capacity of the pile. So it's only the structural capacity. So typically we will limit up the structural capacity to about 85% or 90% as your allowable capacity. So this is based solely on the structural capacity alone that we decided to round it up, like 600 will be 2004 and so on. So this is the structural capacity. Then you need to calculate your pile geotechnical capacity. So here, of course, you need to look into the soil. Like I mentioned before, in Malaysia, we use the semi-empirical method, which is the coloration of SPTN value. So this column here is the depth, and then the red box here is the SPTN value for this respective layer. So, for example, the layer from 0 to 6 meter, the SPT is 4, and then you multiply it by a certain factor. So let's say in this case is 2.5, and then you get your shaft friction. So you total up all the shaft friction that gives you the shaft resistance. And if you have rock, then you have to include in the shaft friction resistance from the rock itself and the end bearing. So this is just to continue on the calculations to let you understand is that, for example, if your pile of 600 millimeters diameter, your pile working load is 2004. So in terms of pile geotechnical capacity, if you calculate your pile shaft resistance and the base, you'll find that you need 28.1 meters length in order to achieve 2,400 kilonewtons. So for 900 diameter piles, you can see that the capacity will be larger, and then you need a longer length in order to achieve the geotechnical capacity for such load. So you do a calculation for different pile sizes, and then you know what kind of length is needed for the respective pile size. And this is just for one pile. Of course, I mentioned before, the site varies quite a bit. So you will then carry out the calculations, for example, for one diameter, using different soil from different boreholes or different boreholes. Then you calculate based on this size or this borehole, what is the length that you need. If you require any rock socket, some may be shorter, you may need some rock socket. And it's quite variable. You can see that from the same site, some you need 28.1 meters, some it's 30 over meters, and some it's less. So you do all the calculations for different diameters of piles, so 600, 900, 1002, 1005. So all this will give you a different length and different rock socket length. So this, of course, there's a lot of calculation, but how do you translate this into a design drawing so that the people at the site can actually construct it? Because if you just give them this table, then it will be quite messy. They will go to the site and say, now I hit 28.1 meters, should I stop? Or if I now hit 31 meters, is that sufficient? So in order to summarize this, we can come up with what we call a detailed schedule for board piles. So for example, like a pile for 600 millimeters diameter, then you can have a table to show what is the required length. So let me just blow this up so they can see it clearer. So for 600 millimeters diameter pile with the allowable capacity of 2,400 kilonewtons, based on the calculation from various ball locks that you have, then you can summarize it in a range like this. So let's say if you roll through the soil, and then if you have the soil before rock, it's about 12.5 to 17.5, then you need to have another 2.5 into rock in order to achieve 2,400 kilonewtons. So some areas maybe you need longer, so you have a shorter rock socket length, and some, if you go deep enough where the shaft has already sufficient capacity to achieve 2004, then you do not need the rock. So with such summary, then it's quite easy for the construction to be carried at the site. So they just need to know this table and then view what level you hit rock, and then they know what is the required rock socket length, or you do not even require rock socket length to achieve the capacity that you designed for. Now, having said that, this is just for one pile. Of course, if you have a different column, comes with different column load, then you need to decide how many number of piles for each column. For example, here, this is a table of showing different columns and their column loads. So take, for example, you need to also check the power group capacity, so power group efficiency. So, for example, if one of the column load is 4,383 kilonewtons, which means that if you're using 600 diameter piles with a pile capacity of 2004, which means that you need two piles because one is 2004, two piles is 4008. So 4008 is sufficient to carry your column load of 4003. And what this means here is that the efficiency, if you're using this configuration, which means that two 600 millimeters per pile, then you have 91% efficiency because of your capacity is actually 4008, but then you're taking a 4003, so your efficiency is 91. But of course, if you want to use the larger power where your capacity is 5005, you can of course take this column load, but then your efficiency will drop. You can see this becomes 79%, less than 80%. Of course, you want to choose the most efficient. So like this example, then this configuration gives you the most efficient group, which is two number of 600 diameter ball piles. So you will then carry out this analysis to find out what is the most efficient power groups for each column. And once you've done that, then you can come up with a construction drawing like such, where you will then show what are the number of piles and which pile size to take the for each columns. And then the construction drawings typically will be endorsed by a professional engineer, and then this will be sent out for construction. Now, besides the foundation drawing, I'd like to let you know that for geotechnical engineers, we are not only issuing out the foundation drawings, we will also have some instrumentation monitoring. So for example, in this site, we have instrumentation, we have surface settlement markers, that is to measure the settlement on the ground surface, and also some of the building settlement markers that are installed into existing buildings. And also deep leveling datum. Of course, if you want to survey, you need to have leveling datum. Now, why instrument is important? So for example, if you are doing construction here, the settlement surface marker will tell you that if the ground is actually settling, whether it's due to your construction or not, so you can start to do something to prevent it further settling. So it gives you an alert. Now, the building settlement markers also does the same thing. So it tells you whether the adjacent building is settling or not. But the other important information from the building settlement marker is that to protect your client for your job site. Why I say so? For example, some neighbors may come over and say that because you are having construction in this site, and then they say that their buildings are actually there's some cracks and some settlements due to our construction. But if you have such monitoring, then you can pull out the record and it shows that maybe during the construction you have record monitor the whole time there is no settlement on their building. So that way you can actually protect yourself and your client. So it's two ways. So the monitoring is important for your own site and also to protect yourself. So that is why we have instrumentation monitoring during construction. So that basically is for the first case study. Then I'll move on to the other case, which I will not go in depth This is for Starry Condominium, just to show you that next door is a Pan Pacific Hotel, where the original design, they've actually designed long piles all the way to the limestone bedrock. So it's long piles and with column, so it's quite expensive. So what we've done here for the Vistari condominium is that we have used the floating foundation system, where we utilize a rough foundation and the piles, so we can actually have a shorter pile, and also to satisfy the building settlement criteria. So this is an example. This is the actual buildings that are still standing today. So for this project, it's actually an alternative design that has reduced the foundation cost by more than 50%, which is a saving of more than 5 million. And where our company got an award merit back in 1998, which was given by ACEM, which is the Association of Consulting Engineers Malaysia. So just to let you know that in terms of power foundations, I can mention the conventional power system. A lot of people would try to actually power all the way to the hard stratum. But if you look into a building on the load distribution, you may see that the load distribution may have higher load in the middle and then less load in the other side of the building. So actually, you can design a building with varying power length. So in the middle, if you have a higher load, then of course you have longer powers. At the side, if you have less load, then you can have a shorter power. So these are the things that you can actually design to be more economical, efficient. Now, this is another interesting case that I'd like to share with you. This tower is actually in Penang, so due to the sensitivity of the case, I would not want to name the name of the tower. But the issue is that initially they found out that the design was inadequate, where the pile is not deep enough in certain areas, so the building settles. But more interesting is that there is actually a dispute on the tolerance of settlement and distortion. And due to this issue itself, the project has been delayed for more than 1 year after the construction has been completed. So you can imagine there's a lot of money involved because of this delay. They finish up the building, but they cannot sell the properties. So the issue is that the engineers, they found that the pile test, they say that it's failed. Basically, they are trying to refer to the JKR specs that generally states limit settlements of 38 millimeters at 2 times working load. So this is the pile test results. On the y-axis is the applied load on the pile during test, and the x-axis is the pile top settlement. So what they say is that the pile has actually failed at 2 times working load. So this pile is RC square piles, it's 400 by 400. So the working load is 220 tons. So 2 times working load is 440 tons. So they then check at the working load. This is already more than 12.5 millimeters, which is again more than what is written on the specs. And the 2 times working load, they say that it's more than 38 millimeters. So here you can see it's over 50 millimeters of settlement at 2 times working load. So they say that it's already more than 38 millimeters. The power has failed. So the point is, what is the definition of failure load? So there aren't many uh, guides or codes that mention what is actually a power failure load. But we found that one which is written by ASTM, or the American Standard of Testing Material, that explains a bit better on what failure load is. Failure load here shows that it's load at rapid, continuing, and progressive movement, which means that if you have a progressive settlement continuously, then you have a fail power. Or the total axial movement exceeds 15% of the pile diameter. So in this case, the diameter is about 400 millimeters, so 15% would be 60 millimeters. So this actually is still within the pile capacity. So the pile, based on this definition, it is still okay. But yes, of course, it experienced a lot of settlement, but it does not mean that the pile is failed. Subsequently, we also been given a set of monitoring data settlement from the building. Now, of course, just to explain the chart again, so on the y-axis is the settlement in millimeters. This is given in log scale. On the x-axis is actually the duration of monitoring over a span of about 3.5 years. So initially, they do not have much monitoring, because normally they do not monitor settlement building. And here you can see there's no reading from level, when they construct level 1 to level 15. Once they face that there's some problems, there are some settlements because some of the areas that the piles were not deep enough. So they have done some underpinning, that is just to add on additional piles. So they already started to monitor. And then you can see that after the underpinning, they've done up all the remedial works. They continue to construct from level 15 all the way to level 38 because they still experience some of the settlement because you are adding additional load. And this first red line here shows where the end of construction, and another one, a few months, then it shows the all the dead load in place, which means that they try to add on the dead load such as the swimming pool. So they add in the water from the swimming pool just to see how the building performs with all the dead load in place. And what you can see here is that the long-term settlement has actually plateaued. Yes, initially they had settled, but at the end, because of the remedial and underpinning, it shows that the buildings is not experience any further settlements. So this also shows that the building is actually safe for use. So this is the one of the case from Penang. Now another one, this one is back in KL in Mont Kiara. Basically, it's a proposed change of a building wall and the position of the basement layout. So this one actually we saved our client of more than 3 million ringgit. So how this is carried out, just to show you on the original design, where they have a 5-layer basement. Next to it is the reinforced soil wall, and then it's supported by piles. So they wanted to use the area on top, so they extend out of the slope and then they construct a reinforced soil wall supported by piles. So this design is quite costly, and then we came in to do an alternative design. And what we did do in our alternative design is that we omitted one layer of the basement, and then we advise the client to extend the building out where we can use the space on the slope. So by imagine removing the soil on this part. So the soil underneath here has actually experienced the weight on top of the soil. If you remove it, and the weight from the building is actually lighter than the soil, so for sure the soil can actually support the structure. So with that, you can actually avoid or omitted the wall, but you can use the space on top, and also you can avoid the piling underneath the wall. And yes, we have reduced one level of the basement, but since you extended out the buildings, we can also make use of the area where we reduce one level of basement, but we still maintain the same car park. So we can still fit in the purpose of what the client needs, and we save the money for constructing the wall and the park. So that also save 3 millions from the project. So that's all for the case study. I'll come to the summary part. So it's probably time to review what we have learned so far. So talk about the importance of preliminary studies on best study, and understanding site geology is important to know the soil condition even before going to the site. And also it's important to carry out proper subsurface investigation, to do proper SI, to do field testing and lab testing to integrate the soil parameters, to know your soil profile so that you can design your foundation. And in terms of selection of suitable pile, bear in mind of cost, time, site constraint, and soil condition. And also I've talked a bit on pile design concepts, and also explain a bit on some of the common misconceptions and some construction issues and the ways to mitigate them, and also importance of vision in terms of construction, and some case histories, and show you how value engineering can be achieved. So the summary is that with proper geotechnical input and design and avoiding common pitfalls, you can actually achieve effective and economical deep foundation. And lastly, for engineers or whatever engineers, not necessarily geotechnical engineers, what you always have in mind is that always think what can actually go wrong at the site and try to mitigate it before it happens. So always think what can go wrong, and also think of whether it can be constructed safely and perform as designed. So if you have this in mind, then you can achieve much better design. So remember to think what can go wrong at site, and whether your design can be constructed safely and perform as designed. So some of the acknowledgement, some of the slides are from our colleagues from GMP. So thank you. So if you have any question, you may do so before we go into the quiz.
Hi, Dr. Gwen. I have some questions I want to ask.
Sure.
First, why in square pi there is a single bar at the center? Is that counted in design or just for handling purposes?
So which
Second one,
there's a
yeah,
single. You're
there is
talking
single
about
bar at the center of square
single
pi.
bar. Is it from one of my slides?
Yes.
Are you referring to this one? I'm not sure which one you are referring to. You can see the piles actually on top. This is fun part, of course. There's no bars on top. So which
Square
one?
pi. Square pi.
Okay, if I go back to the this one.
Yeah.
Oh, that one is actually not. This is for the connection. So when you connect, when you, this is actually for the connection. So this is the starter pile where you have the sharp edge, and then if you want longer length, this is to connect to the pile. So this is not the reinforcement that you're talking about. This is actually to connect to the pile, and then you have to weld the pile. So that's why the joints are actually welded. But at the top of a pile, it's not just one bar. So sometimes you have to expose the reinforcement to connect it to your pile cap. Because normally you have to cut it off at a certain cut-off level, and then you expose the reinforcement bar from the pile. So these are not the reinforcement bar. This is actually a connection.
Oh, okay. Okay. The second one, the hitch head and iron cast fire are what for type of soil? The hitch head and iron cast fire.
Yeah, for normal soil, so you don't use that when you are hitting onto rock. So you if you know that your piles that you're not going into the rock, then you can use those.
And for the third question, what since our my group handle for project overhead bridge OBR, so I want to ask your opinion. What type of file that's suitable for overhead bridge construction?
Yeah, the reality is that I won't be able to answer it. You have to evaluate, okay, your overhead bridge, what is the loading, and then you have to see your soil profile, what kind of soil you're dealing with, or what kind of rock. So you have to analyze the soil properties and the soil profile before you can do your design. So you can't actually immediately say that, okay, this is what structure and then what piles to use. So you have to incorporate all the information to do a proper study and do the design.
Okay. And the last one, how long the instrumentation monitoring is carried out?
Okay, the instrumentation monitoring, it depends on the critical work. For example, if you are in construction, basement excavation or foundation. So if you finish your critical work, that means you know that after this work, whatever you do will not induce further settlement, then you can actually stop. But normally, once you finish your critical work, you will still monitor for another maybe 1 or 2 months, whereas the other work's going on to make sure that there's no additional movement, then you can actually terminate the monitoring.
Okay, thank you, Dr. Gwen.
Thank you. Any other question? If no question, maybe I can move on to the quiz. You can. So for the quiz, you do not need to do any calculation. It's just conceptual. So for example, we are constructing a building of 8 story with 3 levels of basement car park. So we can assume that the typical column load here is about 10,000 kilonewton, or the approximate bearing pressure from the building is 150 kPa. So the question is to determine a suitable foundation system. Now, given you that the information is that it will be an 8 story commercial building with 3 level of basement car park, the approximate bearing pressure from building is about 150 kPa. So if you look at this is just some simplified scenario with three boreholes. So the original ground is actually a sloping ground, and then because of the basement, we need to excavate it for the basement. So the foundation will actually start from the red line and below. So the minimum excavation for the basement is about 8 meters. And for simplicity, we can assume that the SPT for the below the basement is more than 100. And for this exercise, you can assume SPT of 100 for about 15 meters deep, and thereafter bedrock is encountered. So the approximate bearing pressure from building is 150 kPa. So you're asked to determine a suitable foundation system based on the soil profile given. So this is just to show you again on the soil profile. You can scan the QR code to go into the questions. So for the answers, whether are you using or should you use driven piles, check-in piles with pre-boring, or board piles. In case you might not be able to scan this, I will again copy the link to put into the chat. So you have to determine a suitable foundation for such condition where you have a building with approximate pressure of 150 kPa. So let's see how you are doing. Okay, I can see that some are saying that you should use driven piles. Some are saying that you should use board piles. Some of you are saying that no need piles. Yeah. So you can see a foundation starts from this level, which is more than SPT of more than 100. It would be good if more of you can submit in response. Now I'm seeing about 13 responses so far. 15. I can show you. So this is what I'm seeing. So we have 23 responses. This is not the US election. The US election is only red and blue, right? So now we got 4. Okay, 28 responses coming in. Yeah, all vote counts. You have to count all votes. Okay. More and more is saying board piles. Right. Let me get back to the question. So were you thinking whether it's driven piles? Of course, driven piles is not possible because it's too hard to drive in. SPT is more than 100. So that's definitely out of question. Then you think of whether you want to do check-in piles with pre-boring. Of course, you can, but that is not the best option as well. Then you're thinking of board piles. And the truth is, it's not also board piles. The answer is that if you are smart thinking engineers, why you even need piles? I saw that some of you have already chosen the green one, which is you don't need piles. You can actually use shallow foundation or rough foundation. So why is that? Just to show you the preliminary assessment can show you why that's the case. So remember that we have existing ground, and then you need to excavate. So the minimum excavation is about 8 meters for the basement. So in terms of the ground, you can see that the base here has actually experienced about 160 kPa. So typically, you assume that the unit weight of soil is about 20. So multiplied by 8 meters of soil. So at the ground, at this basement level, the soil has actually experienced 160 kPa before. And the bearing pressure from the building is only 150 kPa. That means that the building or the soil has actually experienced less weight. So it's either net pressure onto the ground or less. So the soil will actually take less load than what it has actually experienced before. That is why you actually don't need piles. So the lesson learned here is that it's not necessary that always you need the pile foundation. So to show you uh, figure here says that this is actually a cruise which is multiple story high, and a cruise can float on top of the sea. So more so for buildings, actually we can use floating foundations. So on a final note, with regard to geotechnical engineering, there are no weak soils or rocks, there are only weak engineers, which is a quote from Professor Heinz Brandl, who was a vice president from the International Society of Soil Mechanics and Geotechnical Engineering. So with that, thank you again, and this is the QR code to download the slides. And bear in mind the link is only valid up to 23rd of November. So again, I'll copy the link and paste it onto the chat for you to download. So if you have any question, you can still ask here.
Hi, doctor.
Yeah,
I'm Angela.
that's the
So, our group is doing for the flood mitigation structure.
okay.
And may I know, like, what are the safety steps in ensuring that the soil will not cause the tunnel to collapse, micro tunnel?
Micro tunnel.
Yeah.
So of course, the when you talk about tunneling, I think the most important is to deal with the settlement on top. Of course, if you are doing won't collapse into it, basically removing the soil underneath. So on the top, you may have experienced settlement. So for tunneling, we actually need to do analysis for the tunnels to see what is the settlement that you will have. So if the settlement is excessive, you may have buildings on top, then you may need to check what is the distortion induced from the settlement onto your building. So if that's acceptable or not. If that is not acceptable, then you may need to do some remedial works. For example, you may need to grout the ground, so you pump in concrete to stiffen the ground. That is one way you can deal it. Or you may have additional columns like underpinnings so that you can actually secure your building from further settlements. So the point is that you need to have to do your settlement analysis when you're doing tunneling to see what kind of settlement that you experience and also what is the distortion on the building.
All right. Thank you, doctor.
Hello, Doctor. I want to ask,
Yes.
what will happen if the microtunneling are through a very soft soil condition, and what to solve the problem?
What you solve, like I mentioned, you if you are drilling through a very soft soil, then you probably experience a lot of settlement on the ground surface. So one of the things that we usually do is to do ground treatment. Like I mentioned, if you can drill in some holes to the ground before you do the tunneling, then you grout the ground to stiffen the ground. So when you do the tunneling, then the settlement will be controlled or much less. So that's one of the way, just ground improvement and grouting.
Okay, thank you, Doctor.
Any other questions?
Doctor, so the next question.
Yeah, sure.
Okay, is it possible the excavation failure will happen during the microtunneling?
Failure in what way? You mean the building on top collapse or due to excessive settlement?
Yes, yes.
Yeah, of course. If you, that's why I mentioned that before you start tunneling, you need to have the information on the entire alignment that you are doing your micro tunneling. So you analyze what is the settlement along the tunnel. So if there is, I'm sure there will be settlement. So if that settlement, if it's a green field, meaning there's no building, then probably it's still okay depending on what kind of magnitude of settlement that you're experiencing. If there's building, whether the distortion due to this settlement will affect the stability of the building. So, of course, an engineer, you need to analyze all this. If you know that the building will experience severe distortion, then you need to do something before the tunneling. So this all needs to be designed for during the entire tunneling project. So you're not just designing for the tunnel itself, but you need to take care of the buildings on top along your tunnel alignment.
Okay, thank you, Doctor.
Mhm. Any other question?
Dr. Gu, just one from
Yeah,
me.
Farah?
Uh, Based on your, I just want to know your opinions. You can see that there's a lot of close. I mean, there's a lot of high-rise building close by in Kuala Lumpur area,
Right.
and and that's as if you ask as a layman, it seems like there's like empty soil already downstairs. Everything is full of piles and foundations. What is your opinions? I mean, in terms of stability of the soil itself, and as an engineer, how do we look into this? I mean, do we consider? I mean, of course, in my opinion, if one building starts shaking, that's influence the other foundations. So how do we? How what is your suggestion, or what is your opinions in this case?
So you are talking about just purely looking at the foundation. You're not talking about tunneling in the area where there's a lot of buildings, is it? Or you're actually referring to tunneling?
I mean, as a layman, it seems like empty down there already. Everything is full of files, and then we do more tunneling. And I just wonder if the soil is still there. I mean, if the soil will not affect the existing foundations.
Yeah, of course, the soil is still there. So if you do, for example, board piles, then you actually replace the soil into your concrete piles. If you are using driven pile or checking pile, then you actually displace the soil. So the soil underneath is still there, but when you have your piles in the ground. So if you are doing tunneling, it's very important that your tunnels does not hit the pile. So that is one thing, you do not hit the pile, but that means that you need to know what's the depth of the piles in the ground. So you can see why some of our MRT tunnels or the stations have to go so far deep. That is because we want to avoid those piles. So that is why the tunnel has to go so deep, which is actually below the piles. And for geotechnical engineers, we actually have to do the analysis, evaluate, to carry out analysis to check what is the influence of the tunneling to the existing foundation. So if you go too close to the pile foundation, one thing is that the load from the building will transfer to your tunnel, or the other thing is that when you tunnel through too close to the foundation, you may affect the stability of the building. So you of course have to do a proper analysis to evaluate any safety issues. So and proper analysis needs to be carried out when you are dealing with tunneling close by all the building foundations.
In general, what is the spacing? I mean, what is the distance from the pile and the tunneling outer layer? The minimum that normally by practice.
In practice, we would definitely say something like two times or one times diameter of the tunnel itself. But that is
Oh,
just start off. But you have to carry out the analysis to make sure that the induced stresses from the tunneling and how it responds to the building, and vice versa, how the loads from the building transfer to the tunnel.
no.
But this is talking about existing buildings and then you do tunnel. But for example, the other scenario is that now you carried out a tunnel. So
Mm,
now, for example, you have line MRT line 1 and line 2. And what happens if you want to construct a building next to a tunnel?
mm,
So that is a different story where the railway X comes in. So then you have to be uh, a certain distance away from the protective zone. So that in the railway X, they spell out the certain distance as the zone 1 and zone 2 as the protective zone where you cannot have buildings next to the railway. So the tunnels are MRT tunnels, they are railway under the Railway Act.
oh, okay. Well, that's remind me of London Underground. That's why they go seven floor down, isn't it?
Correct, yeah.
That to avoid the foundations of other buildings.
That's right.
Uh, all right. Thank you. Thank you. Okay.
So for line two now, I think the deepest we go, it's the tunnel is about 50 over meters underground.
Oh, 50 over meters.
Yes.
What? Oh, how many stories is that? 50 over meters.
So per story is about three, let's say 3 meters, so 50 over meters, you have to about 17 stories underneath.
Oh, that's really deep. All
Yes.
right.
Any other questions?
Any other question, guys?
If no question, I can just show you the one last slide. It's just to share with you on what our company is all about. So this is actually a video that we have for our 20th anniversary. So we have a better idea on what we actually do. So GMP is actually what we call a one-stop consultancy service center. So it's not just doing geotechnical. So we have other specialist company doing structures, highways, M&E as well. So this QR code links you to the YouTube video of our company. So that's all. Thanks again for your concentration throughout the talk. I hope you have learned something that would be useful for your design project.
Thank you so much, IR Dr. Gray, for your valuable insight on geotechnical engineers in a construction project. We have come to the end of our talk session. Once again, thank you, IR Dr. Gray, for your enlightened speech. We hope that the session has been educational for everyone and hope that it will benefit us all. Thank you for your time and Assalamu alaikum.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you, Doctor.
Yeah,